Okay, so I want to talk about band theory. So we've been talking about the physical properties of these metals. I want to talk about the electronic properties of these metals. And this is when we can get into band theory. And this is more relevant to what we've been talking about recently with molecular orbital theory. So band theory is just an extension of molecular orbital theory. And it allows us to explain the weird properties of metal, the multi-center orbitals that spread over the entire molecule. So just like in molecular orbitals where you have these molecular orbitals that spread over the entire molecule, you have orbitals in metals that spread over the entire metal. You can't really construct a model of localized bonding in solids unless it's something, well, even with diamond where the bonds are covalent, it's hard to define the molecular orbitals. That's where we get into band theory. We still think of the bonds in diamond, where you have carbon-carbon bonds, as multi-center bonds. This is the multi-center orbitals that spread over the entire crystal. Okay, so let's look at a lithium crystal. If I were going to draw just one lithium by itself, it would just be an s orbital, right? It would look like this, and it would have one electron. If I put two lithiums together, I would get two orbitals, and I'd have two electrons, and I would have a bonding orbital and an anti-bonding orbital. And if I drew what the orbitals look like, you'd have a bonding interaction, so two of the s orbitals would be constructively interfering, two of them would be, and then the other two would be destructively interfering. And here now I have a difference in energy. So we're going to focus on the difference in energy between the HOMO and the LUMO. If I have three lithiums, then I get three molecular orbitals. And they might look like that. If I have four lithiums, again, I'd have four molecular orbitals. Notice how, while I'm drawing these diagrams, the difference between the HOMO and LUMO energy levels is shrinking. So if I just had four lithiums, my HOMO-LUMO gap would be here. So every time you add a new atom, you're adding another orbital that's going to close the gap between the HOMO and the LUMO. So when you have a metal network where you have just a whole bunch of metals together, this is what we think of as a band. And so if you have, Li to the N, whatever, a whole bunch of them, the orbitals are so close together that they look like a band. And so we draw it like this. And for however many, so with lithium that just has one electron, if you have N lithiums, you have N orbitals. Because in lithium we're just dealing with the s orbital. So there's one orbital for one atom. And those orbitals are going to be half full in lithium because there's only one electron. So the way that we show fullness is we basically shade in the bottom half to show that there's electrons in the bottom half of that band and the top half is empty. So because these energy levels are so close and they're not all populated in the ground state, some of the electrons can easily move up to the empty orbitals. And this is what gives electrical conductivity. It's a characteristic property of things with partially filled bands. So at 0 Kelvin, this is your ground state. At any temperature above Kelvin, you will have some electrons promoted up into the top half of the band, and that's what gives you electrical conductivity. There's a node there, right through the atom. So before we move on, I just want to point out, again, we're dealing with an oversimplified model. In a lot of metal ions, we have S and P and D orbitals. And when it comes to metals, a lot of the times those orbitals are all mixing together. So this is a very simple model. And if you're going on to graduate school or maybe some classes at Notre Dame that are dealing with material science, you'll probably learn a much more complicated model. But this is the simple version. So it fails a lot. But we're going to use it to explain some things. So I just said that conductors conducted electricity because of basically because their bands are half full. There's another way to get a conduction in a solid. So conductors in general are things that conduct electricity, obviously, but they don't have to just be things that have partially filled bands. I'm going to make this blue. Okay, so conductors look like this. They can either have a partially filled band, like we just said, and what that means is that there's no energy difference, or there's no big energy barrier for electrons to be promoted. Another type of conductor is where you have, so up here, if we would have drawn a band for lithium-4, because this had a band gap here between the HOMO and LUMO, you could have said that there were two bands, an empty band and a full band. Sometimes the empty band will overlap with the full band. And these two different types of bands have names. The one that's full is called the valence band, and the one that's empty is called the conduction band. So you can have a conductor in two situations. Either you have a partially filled or a partially occupied band because you have something like lithium where you will only have one electron for each orbital. Or you can have a band where the valence band is full and yet there's another band above it. Like let's say the valence band in this case was the s orbital and the conduction band would be the p orbitals. And then there's some mixing there. So the biggest thing is here that you have no band gap. So it doesn't take a whole lot of energy for electrons to be transferred from a lower energy to a higher energy. This is contrary to an insulator. So let me show you what an insulator looks like. I bet you can guess. Things that are insulators have very large band gaps. And it turns out a lot of the times it has the difference in the band gap energies have a lot to do with the covalent nature of the bonds between the atoms or ions. So in metals, the bonds are not covalent, they're not directional. They are more of, we think of metals as like a sea of electrons. Here. This is literally what we think of when we think of metal ions. So you have basically these positively charged nuclei just kind of floating in a sea of electrons. They're not necessarily covalent bonds. Whereas something like diamond, where all of the bonds are in fact covalent bonds, and they're not quite as promiscuous as they are in metals, those are situations where you have a large band gap because you have a large drop in the energy of the bonding orbitals compared to the higher energy anti-bonding orbitals. So you have a very large band gap here. So this is something like diamonds. Diamond is a really good insulator. And then we have something in between. And this is where things get really interesting for materials and electronics. So in the middle, you might have a band gap, but it's small. And these things are called semiconductors. When you have a semiconductor, this thing will not conduct electricity unless you add enough energy in the form of heat or voltage to pop electrons up to the valence, from the valence to the conduction band. So semiconductors are things that do not conduct at certain temperatures or at lower voltages, but when you pop the voltage up or when you raise the temperature, then you can have occupation of that conduction band. And so these are things that we use in electronics because they offer us some control. An interesting difference between conductors and semiconductors are that semiconductors increase conductivity with higher temperatures, whereas metals actually decrease their conductivity with higher temperatures. And the way that we explain that is that if you imagine the electrons trying to jump from metal to metal into different metal orbitals, And the higher the temperature, the more the metal is vibrating. It's harder for the electrons to actually move within the metal lattice. So that's why the metals they have an inverse relationship with heat and conductivity, whereas semiconductors have a direct relationship. One other thing I just want to let you know, so whatever level the electrons are at 0 Kelvin, it's called the Fermi level. So you might hear that term from now and then. So basically, it's just the ground state of these bands. So let me just give you a couple examples. I'm going to compare carbon, silicon, germanium, and tin. And these are things that are all in the same family of the periodic table. Actually, I have a slide for this. Let me grab it. So carbon, silicon, germanium, and tin, they differ a lot in their unit cell, like the size of their unit cell, and the actual energy between the bands. And so, actually, let me write this down, because I have some different data on my notes here. So the element, I want to talk about the band gap. And that's what was on that table, except it was just written in different terms. So this is electron volts. So you can see that the difference between a carbon band gap and a tin band gap is it's big. So carbon is a complete insulator and tin is a conductor. The two in between here, silicon and germanium, are semiconductors. The bond strengths differ, as you might be able to guess. Whereas carbon has the strongest bond, it's 346 kilojoules per mole. Tin has the weakest bond. Carbon has the most covalent nature, it has the largest band gap. Tin has the least covalent nature, it has the smallest band gap. And then the cell length is representative of that bond strength. So carbon has the shortest, strongest bonds. It has the smallest cell length.
Number that was like 5.5.
Yeah, I don't know. That's a good question. There probably is. But it would depend on the temperature and the voltage that you're putting through it. But I don't know. I don't know what that cutoff is. I do want to talk about the type of semiconductors that we have. So silicon and germanium are things that are semiconductors by themselves. They are intrinsic semiconductors. In other words, in their pure form, they are semiconductors. So you don't need to do anything. You can just have a silicon chip, and that will act as a semiconductor. The bands look like this. So at room temperature, you would have your valence band almost full, but some of the valence electrons would pop up into the conduction band. And what this does is it leaves holes in the valence band. Both the holes and the electrons in the conduction band move. So we think a lot of the times you'll hear people talking about holes moving or electrons moving. But technically both of them move. So let me pop out my slide again. So here's just a cartoon of silicon. So at 0 Kelvin, you don't have any electrons popping into the conduction band. So all of the silicon atoms are, they have their covalent nature and they have all their electrons. But at ambient temperatures, you can have some electrons popping into the conduction band. And so here we have, you can see a silicon with a hole, and its electron is over here on this silicon. So basically the electrons move around. So this electron is in the conduction band, and there's a hole in the valence band. Now, engineers play around with the composition of their semiconductors to get properties that they prefer or they desire. And this is when we start talking about extrinsic semiconductors. And these are things that their properties have been modified by doping or by adding impurities into the silicon or the germanium. So the semiconducting properties can be modified by doping. And you don't need very many impurities. So you can add impurities where you have only one atom in every million atoms that's an impurity. So if you have one in, you need less than or equal to 1 in 10 to the 6th impurities. That's what's needed to alter the properties. Where? Oh yeah, it would be, yeah, I think you're right. Yeah. Oops, I ran over the page. So this is one reason that if you are making a semiconductor, if you want the properties of silicon or a pure substance, it has to be really, really pure, because 1 ppm gives you different properties. 1 ppm of impurities. There's 2 types of semiconductors. There's the p-type and N-type. P-type, P stands for positive, N stands for negative. In the p-type, you have a bunch of extra positive holes, essentially, and the N-type you have negative or extra electrons. So the p-type, an example of this would be Ga, which is next to gadolinium, which is next to germanium, so it's 1 unit to the left, and you can dope it with silicon. So it would be silicon doped with Ga, not the other way around. I'll tell you. What? It's doped with silicon? Well, let me tell you why I think it's silicon doped with gadolinium. So if your band looks like this, okay, and let's say this is a semiconductor, so there's a band gap, but it's significant enough that it's not the best semiconductor ever. If you add an element, so in this case, like let's say we take silicon and we add an element that has 1 less valence electron. So gadolinium has 1 less valence electron than silicon, right? Even though they're not in the same valence shell, gadolinium has 1 less electron. And so what you end up doing is you add another empty orbital or another empty band. So this thing is called the acceptor band or the acceptor level. And so an example of this is substitution of group 14, which is carbon, silicon, and germanium. Substitution of a group 14 element with group 13. And what that does is it introduces this discrete energy level and that is unoccupied, and that leaves positive holes in the valence band, because now the electrons can hop up to this lower energy band, and you get, I'm going to erase this now, you get holes in your valence band. So there's holes here that I'm circling, and then you have some of your electrons in the acceptor band. So I'm not sure if I was clear with that, but the Fermi level is now right there. And now you have conduction-like properties where holes can move and electrons can move as well. So let me show a slide. I think I have that as my, nope. There's my p doping. So here's an example where you would take silicon and add one aluminum atom. Right? So if you add an aluminum, now there's a hole. And that hole can move. So like it can steal an electron from this bond over here. And then that hole has moved. So the electrons are moving, but you also can say that the holes are moving. The N-type is similar but opposite, where you are actually doping with some, so if you were talking about group 14 being your main component, you would dope with group 15. So you'd add an element with one valence electron. So N-type is, an example is substitution of group 14 with group 15. And what this does is it introduces extra electrons, or it introduces a discrete energy level, which is called the donor level. So here, this would be my normal situation, not doped, and now I've added another donor level. Whoops. I'm going to add it up here closer. And now your electrons can travel from the donor level to the valence, from the donor level to the conduction band. So now the band is acting as a charge carrier, and this is when, so here's an example, where you have a phosphorus, silicon doped with phosphorus, so that phosphorus has an extra electron. When the electron moves to a silicon, the phosphorus has a hole. So once again, you can talk about holes moving, but a lot of the times when you're talking about N-doped, which is negatively doped semiconductors, then you talk about electrons moving. And so these things are really useful, especially in p-n junctions. So p-n junctions are where you take a positively doped semiconductor and you smack it right upside a negatively doped semiconductor. And this is the basic building block for LEDs, so light emitting diodes, transistors, and a bunch of other things. And I forget what they are, but a lot of electronic devices use these p-n junctions. So I had a video here and it seems to be gone. That's okay. So what happens here, so there's two situations. So if you have a p-n junction where your p is on over here on the left and the negative side is on the right, if you apply a negative potential to the negative side, you'll basically fill up the electrons in this side, and they will go over to this. And basically your electrons will keep moving this way, and then the holes will move this way. And you get current flow. So that's a way to get current flow. And then you can stop current flow by applying an opposite potential. So if this were just a wire, you couldn't shut off the current flow by just reversing the potential. But if it's a semiconductor, when you reverse the potential, the electrons move this way, the positive poles move that way, but nothing happens here, and you stop the current flow. So that's why these p-n junctions are really useful. The way it looks, let me show you. So if you have a p-n junction, so let's say I'm just going to draw the P here, so it has a positive hole, and it's got some electrons there, and I'm going to draw the N doped right next to it. So N has the negative doping or donor band. What happens when you pump electrons into the N? So if I'm putting electrons into this side, I start filling up this initially, but then they fall. Remember that there's holes down here in this P band. The electrons will fall down, and when they do that, they give out light. So depending on what the difference is between this, the conduction band on the N-type and the valence band on the P-type, you will get monochromatic light. And this is what an LED looks like. I'm going to go grab my LED because I forgot it. I'll be right back. The orange. Oh, okay. So, I've written on this index part the actual, so I looked online and they don't actually tell you actually what they're made of, but the red is gallium arsenic phosphide. So it's not just it's not just one thing doped with another, it actually is complex. And there's like 20 years of engineering that goes into these, like to figure out which color or which compounds will give you which color. But what I thought was interesting is that it's the green and the blue. So green is 525 nanometers, and the blue is 470 nanometers. But they're made of the exact same material. They're both silicon carbide with gallium nitride. And what you can do is you can actually tune the color, no matter what the band gap is. You can tune the color by adding voltages at a certain thing. So, like, let's say I was doing a voltage of 1 volt. Okay, 1 volt will give me energy or electrons at this energy level that will fall down. But you can do maybe 2 volts, and then 2 electron volts here will give you a different wavelength. So you can actually tune the wavelength with the same material. You can tune the wavelength based on the voltage that you apply. So the red and the green, although they're the same material, they have a different voltage applied. So one of them is like 1 volt, one of them maybe 1.2 or 2 volts. Cool, huh?
Yeah. Those look special, or are they just like...
What?
Those look special
What do you mean?
things, or are they like just...
Those are LED, light emitting diodes. Oh, so a diode is the PN junction, okay? And it emits light when you apply the correct voltage because the electrons are populating these higher energy bands in the N-doped semiconductor. So we have the N-doped smacked up against the P-doped. So the N-doped has the higher energy electrons. When you apply a negative voltage to that side, you're basically pumping electrons in there. So you fill up these higher energy orbitals, and then they fall down into the P-doped side. They literally fall down. And when they fall down, they give off a photon because they're losing energy in the form of light. And that's what gives you the light that you see in LEDs. So when you go and you buy an LED for Christmas lights, or now they're making LEDs for house, like regular screw-in light bulbs, they're made of these PN junctions. The full spectrum ones, I don't quite understand yet, and I think they're more complicated. So they don't have monochromatic light; they have full spectrum light, and so it must be either a mixture of different lights, or I don't know. They're kind of a new thing, so I don't think they're anywhere in our textbook. But those are kind of the newer LEDs. The blue. So for a long time they were having trouble getting blue light. I think a couple of years ago when I was TAing at Duke University for this class, we didn't have blue LEDs because they hadn't figured it out yet. But then somebody engineered blue LEDs, and now they're like they're Christmas lights and everything. And then they came out with the full spectrum ones, so we can use them in more practical purposes. They're really low energy, so you don't need a lot of energy to put the electrons in these higher energy orbitals, and that's why they don't spend as much energy like just through operation as a regular light bulb. You don't lose a lot of energy in heat, and you don't use a lot of energy to populate those higher energy orbitals. So I think that should get you through your problem set. So there's a couple questions on semiconductors.